Very good evening, all of you. I think I'm going to take us over the finish line. I'd like to thank PMWC for this opportunity. And I like the fact that we are sort of bookending today's day because we started the morning with a talk on fragmentomics, the presentation by Delphi. And I'd like to talk more about how ClaretBio is adding to this whole storyline of using cell-free DNA fragmentomics using our flagship library preparation technology seriously. This is a mouthful of a title, in agnostic, low-depth sequencing-based approaches for liquid biopsy diagnostics. I'm sure you guys are familiar with a workflow of this sort, where you're looking at a standard cell-free DNA-based diagnostic workflow. You start with sample collection, cell-free DNA extraction, library prep. There may be some form of targeted enrichment, or there is whole genome sequencing, followed by capture of features. Usually you're looking at a variant panel, a set of mutations, and so on, going into reports. But cell-free DNA is more complex than that. We know that there are several mechanistic factors that contribute to the formation of cell-free DNA. There is cell death, apoptosis, DNA repair, circulating extracellular nucleases that chop up your DNA into different pieces. And this is determined by underlying factors such as nucleosome positioning, transcription factor binding, underlying methylation, and chromatin state. When you look at a typical plasma cell-free DNA fragmentation profile, there are nuances. There is a single peak at 165 base pair, which is reminiscent of binding around a histone. Then there is also a shoulder around 144 base pairs. That is the histone core. And then you see this, a periodicity of about 10 base pairs, which is indicative of DNA's nicking activity at the minor groove in the helix. So this has sort of led to the formation of this new emerging area for biomarker discovery, where you look at fragmentation pattern. And there are two different approaches here. You could either look at fragment length, or you could look at fragment end-motifs. And there have been several papers around it that have looked into these biomarkers. However, if you want to do cell-free DNA fragmentomics, there are several challenges with traditional library preparation method, that is low molecular conversion. The limitation of standard library preparation method is that there are these highly degraded fragments which are found in both in cell-free DNA and in FFPE, such as nicked DNA, single-stranded DNA, and ultra-short DNA, which have information that can be worked on. So in a traditional library preparation method, you have end repair and detailing, which generates blunted molecules. And then there is ligation of double-stranded adapters. But because of this modifications, what these methods capture are full duplexes. They can capture a single intact strand in a nicked duplex molecule, but they never capture single-stranded DNA, and they're not efficient in capturing ultra-short DNA. And they also lose native end information. So with our technology, we sort of address these issues. With seriously, the first step is denaturation, where you denature every molecule into single strands. And these are ligated by these specialized splinted adapters, which hybridize to ends of DNA and capture your DNA without any end repair or detailing. What this means is that you're capturing the nicked DNA, single-stranded DNA, and ultra-short DNA that are typically found in these challenging samples. The workflow is pretty straightforward. It's a standard library preparation workflow. You could also add UMI. So if you are doing normal targeted enrichment downstream, there is optional UMI steps. But there are certain salient features of seriously. One is that you generate libraries of higher complexity. So the fact that you're retaining all these additional molecules, your complexity is much higher. The graph shows a comparison between seriously and a standard double-stranded prep. Because of the capture of nicked and ultra-short and single-stranded DNA, your complexity is much higher. They also retain relatively shorter fragments. So here I'm showing a comparison of libraries generated with plasma cell-free DNA versus urine cell-free DNA, and you see that seriously is able to capture fragments that are less than 100 base pairs. And then it also retains native ends. Here I'm showing a graph of base compositions at end of DNA. The top panel is seriously, bottom panel is a double-stranded prep. What you see here is that the forward and reverse reads have different base composition for seriously, whereas with double-stranded DNA, they're actually complementary or mirror images of each other, which is a function of the blunting that happens in standard library preps. So with that, I propose an updated cell-free DNA-based diagnostic workflow where you start with your library prep, but you use seriously, retain all this information, and then you go into fragmentation profile. So I want to show two different cases where we've demonstrated the utility of our technology. One is a myelodysplastic syndrome cohort. It's a collaboration with Professor Azra Reza at Columbia University, where we've looked at fragment length. And then the other cohort is an indolent prostate cancer cohort in collaboration with Dr. Javed Siddiqui at University of Michigan. So myelodysplastic syndrome, as you know, is a hematopoietic disorder where it starts with abnormal morphology and composition of blood cells, and it can progress into AML. So this is the cohort setup. We had about 132 samples, extracted DNA from approximately 1 ml of plasma. We used about 1 nanogram of DNA in our library prep. We did both shallow and deep sequencing and did our analysis. The analysis that we did here is similar to what is done in Delphi, where we look at the raw data, we do mapping and quality filtering, and then we line up these fragments into short and long fragments across a 5 megabase pair bin across the genome. Here, long is 100 to 150 base pairs, and short is 100 to 150 base pairs, and long is 150 to 200 base pairs. And what we wanted to do is we wanted to take it a little further and see, is there additional information in this? So we wanted to see if cell-free DNA fragmentation can reveal underlying chromatin states. As you know, the nucleus is organized into open and closed regions, or A and B compartment. These regions are sort of fed in by underlying nucleosome positioning, where you have sparse positioning with open chromatin and closed nucleosome positioning in closer positioning in B or closed chromatin. However, this is the same thing that also regulates cell-free DNA fragmentation patterns. So we wanted to see if we could combine these two and reveal underlying chromatin states using this low-depth sequencing approach. To do this, what we did was we took the AB boundaries determined by Hi-C from GM12878, and then we lined up the short to long fragment ratio in a 250 genomic bin in that 5 megabase pair window, and then we looked at this ratio within this window. So on the top panel, you're looking at a representative healthy sample. Here you see that the open and closed compartment have different average ratios. However, when you look at MDS, you see that this ratio is different. The ratio between the open region and the closed region actually get closer to each other. So this shows, this is an indication of some form of reorganization of the chromatin structure itself. We looked deeper into this and we saw that there is some association with subcompartments of sub-AB compartments, and we found that the regions were depleted for nucleolar associated domains and also condensed chromatin. Looking further into the cohort, we saw that this signal was actually predominantly found in MDS-RS, which is a subtype of MDS. RS stands for ring sideroblasts. This is typically detected by bone marrow biopsies, by histopathology, with the heme ring around the nucleosome. And this structure is formed during abnormal enucleation during erythrocyte maturation. And this is associated with defective chromatin condensation. fragmentation, which in turn results in abnormal fragmentation. Here, what we've shown is evidence of a histopathological signal that has been captured in liquid biopsy by cell-free DNA fragmentomics. So the next part of my talk, I'm going to talk about prostate cancer. Similarly, a cohort which had both healthy and prostate individuals. We used about 500 picograms to 1 nanogram of input and did fragmentomics. But here we are looking at end profiles. So we are looking at the k-mers at the end of cell-free DNA fragments, both at 5' and 3' ends. And we counted either 1 mers, 2 mers, 3 mers, and so on. And we did machine learning analysis on these. We did k-fold analysis, random forest, and so on. We do see a good separation between healthy versus prostate cancer in this cohort. Looking further into it, we saw that the performance of 3' ends was much better than 5'. And may I remind you that with seriously, you're actually retaining the 3' ends in comparison to other methods. When we looked at the performance of this classifier, we saw that it worked really well with prostate cancer. However, when we tested the same classifier with another cohort which had mixed cancers, it did not perform as well, showing that this is specific for the disease. And then we also saw that the signal was captured at very low depth, where even at as low as 100,000 reads, we are retaining the signal, and that the signal is spread across the genome. With that, I'd like to summarize. In MDS, we saw that the cell-free DNA fragment length has a strong signal of epigenome reorganization. And on the other hand, with prostate cancer, we saw that there was a unique genome-wide 3' end motif in cell-free DNA. And the common thing between both these analyses is that the signal is captured at very low depth of sequencing, 5 million reads, using 1 nanogram of DNA, which we extract from as low as 500 microliters of plasma. So it's much lower than the requirements of traditional NGS methods. So showing that cell-free DNA fragmentomics can be used as an agnostic, cost-effective diagnostic method in cancer. With that, I'd like to acknowledge the folks who have contributed to these analyses, Camille Schwartz, Tobin Groth, and Andrew Mission, and then our collaborators at Columbia University and University of Michigan, and then a shout out to our very small but very strong team down at Scotts Valley. We do our R&D production, all of us together, down closer to Santa Cruz. And we have a booth right across. Do stop by for conversation, for trial kits if you have collaboration questions, or write to us at info@claretbio.com. Thank you, everyone.